Hi, welcome to Great Basin College and Geology 101. I'm your professor, Caroline Meisner. I'm excited to work with you this semester, and in the next slide or two, I'll introduce myself and then we'll move on to Geology 101 content. This is a photograph of my family, my kids Wayne, Kate, and Zachary, and my husband Dave. I really enjoy spending a lot of time outside. That's one of the things that led me to be a geologist. Throughout the semester, I'll be showing you lots of photographs from places I travel, including I've been to Iceland, and the photograph on the left is of a volcanic landscape in Iceland. So you'll be seeing lots more photos of Iceland over the rest of the semester. The photograph in the top right is in a glacial landscape and a currently glaciated landscape. The landscape that you see behind me is an example of a past glaciated landscape. Those giant boulders are glacial erratics that have been transported by glacial processes. And then in the lower right, I love to swim and I love being on the water. And at the beginning of this semester, I'll be recording many of the lectures from northern Minnesota. That's where I am in that bottom right-hand corner on a lake in northern Minnesota. And it's just now starting to rain, so I might have to finish recording this lecture inside, but we'll see what we can do, and hopefully I can stay outside a little bit longer. Take a few minutes to consider the word geology. What does geology mean? Okay, so when you think about geology, what do you think about? And the second question I want you to consider is, why is geology important? So take a few minutes, take a few notes on why you think geology is important, and then see how your notes compare to what we discuss in the next few slides. One of the main reasons why geology is super important is because of all of the geologic resources we use to support our modern day lives and society. If you just take a look at a simple pencil, you can see the amount of limited or non-renewable resources that are involved in the creation of a simple traditional pencil. Okay, so petroleum products are used to develop the eraser. The metal clasp at the top holding that eraser onto the pencil is made of zinc and copper, so metallic resources. Iron was used to form the machinery that allows the pencil to be created. Paint pigment, clay, and minerals like graphite are used in the creation of a pencil. So in something so simple, there are lots and lots of resources that are used. And like I said, most of those are non-renewable, except for the wood that makes up the stem of the pencil. We gather these important geologic resources through resource extraction. So we'll use oil to help energize our world, whether we use that oil in cars or industry or transportation, other types of transportation. We use coal to help with the creation of electricity, so coal burning power plants. And then, of course, metal extraction, like the important gold mines in northern Nevada and other mining activities throughout our state. So these are all examples of resources that we use on a daily basis in our normal everyday lives. Another important aspect of geology is learning about geologic hazards. Geologic hazards are those natural disasters that impact humans or impact our infrastructure. Some of you may have experienced the 2008 earthquake that occurred in Wales. It was an incredibly destructive earthquake for especially the historic area in Wales. Now, fortunately, there were no fatalities in that Wells, Nevada earthquake. However, earthquakes can be extremely dangerous and fatal, such as the Haitian earthquake that occurred in 2010 that eventually took 300,000 lives. Now that number, in addition to lives that were taken immediately with the earthquake, but it also includes deaths associated with a cholera epidemic that stemmed from limited freshwater resources following the tragedy. Another type of geologic hazard includes volcanic eruptions. The 2010 Icelandic eruption of E13, I have a really hard time pronouncing the name of that volcano, so I will refer to it as E13. So E13 is pictured here, and this particular natural disaster ended up shutting down air travel in all of Europe due to the volcanic ash. And so the volcanic ash can cause visibility issues. It can clog up engines in planes, and it can damage airplanes in other ways as well. Plus, with this type of eruption that releases so much ash, the agricultural lands in Iceland, where the ash settled, and perhaps even ash settling in Europe following the jet stream, greatly impacts agricultural practices. Another type of geologic hazard is a tsunami. Tsunamis are related to earthquake activity on the ocean bottom. On the left-hand side, we have a photograph of some of the devastation of the Indonesian tsunami of 2004. And on the right-hand side, there's a photograph of a tsunami in Japan from 2011. One of the important things to learn about tsunamis, and we'll talk more about them when we get to the chapter on earthquakes, is that many of the deaths associated with tsunamis are caused due to curiosity. So when a tsunami is approaching, right before the large towering tsunami wave reaches the coast, the ocean water actually recedes. It goes far, far back, and it exposes the ocean bottom that normally isn't even exposed during low tide. So folks that don't know much about tsunamis often are curious and go out onto the beach and walk down into the area that's newly exposed, and you can see fish flapping around, potentially exposed coral, shells, and other seafloor features. And then shortly after that, the large tsunami wave approaches and engulfs all of those people that were beach combing. So if you ever are in a coastal area and the water recedes, immediately get to higher ground or get to a building that's tall and very, very sturdy. Throughout the lecture notes, you'll discover that I have learner outcomes for each chapter kind of sprinkled throughout the entire lecture. Okay, so here's an example of one. Distinguish between physical and historical geology and describe the connections between people and geology. Well, when we were talking about geologic hazards and geologic resources, we were talking about the connections between people and geology. We can also include information about the importance of soil and the importance of our water resources in our connection with geology. So over the next few slides, or I think just the next slide, we'll talk about physical and historical geology. Oh, and one other thing. With these learner outcomes, they're a great way to study for your weekly quizzes. So what you can do is after you finish a lecture and after you've done the homework assignments for the chapter, you can go back through your PowerPoint and respond to these learner outcomes. So you'll be able to then describe the connections between people and geology, so you can use the lecture notes to help self-check your responses. And you'll also be able to distinguish between physical and historical geology. So use these as a self-check mechanism before you take your quizzes. Let's get a solid definition of geology. Geology is the science that pursues an understanding of planet Earth. There are two kind of really broad categories about or broad aspects of geology: physical geology and historical geology. Physical geology is the topic of this particular course, where we will examine Earth's materials and also processes that operate on our planet. So internal processes like plate tectonics and surface processes like those processes that shape the surface of the Earth on a daily basis, like stream processes, shoreline processes, mass wasting. So mass wasting is when you have landslides, glacial processes. So we'll talk about how these glacial erratics were deposited as ice melted and ice transported rocky material. And then with historical geology, which we will touch on only briefly in this class in a chapter on geologic time, historical geology looks at the origin of Earth and its development throughout geologic time. If you're really interested in geology and pursuing geology, I encourage you to take Geology 102, and that's the historical geology is the topic of that class. Okay, here's another one of our important learner outcomes for Chapter 1. Summarize early and modern views on how change occurs on Earth and relate them to the prevailing ideas about the age of the Earth. Now, this is going to be probably the last learner outcome slide that I actually read. I want you to make sure you focus on them, though. Just because I'm not recording on these slides doesn't mean they're important. So make sure you take some time and look at those learner outcomes. Humans have been studying the Earth for centuries. And there have been really interesting developments in the field of geology throughout time. And there are a few different beliefs about geology that I want to discuss. And the first is catastrophism. And that's the belief that Earth's landscapes were shaped by catastrophes. And this was a belief that was held during the 1600s. So with catastrophism, large catastrophes like Noah's flood would have been influential in the development of places like the Grand Canyon. So with catastrophism, the belief of catastrophism, the Grand Canyon would have developed over a very short amount of time, a number of days. Whereas the belief of uniformitarianism, now that's a tongue twister, isn't it? Uniformitarianism. This was developed by the father of geology. His name is James Hutton, and we'll be talking more about James Hutton throughout the semester. With uniformitarianism, it's a belief that small forces over long periods of time create substantial features like the Grand Canyon. So uniformitarianism would assert that the Grand Canyon has taken a very, very, very long time to form. So with uniformitarianism, it states that the physical, chemical, and biological laws that operate right now on our planet have operated throughout the geologic past. And kind of the saying that goes along with uniformitarianism is the present is the key to the past. So we can look at shoreline processes. We can look at how sediments are deposited in an ocean. We can look at glacial processes, and we can translate that to what was happening thousands of years ago, hundreds of thousands of years ago, millions of years ago. So with uniformitarianism, it means that small forces over long periods of time create substantial features like mountains and canyons. Okay, so mountains were not lifted up in 1 or 2 days. Mountains have developed over millions and millions of years with gradual uplift increases prompted by seismic activity or earthquakes. Canyons like the Grand Canyon developed very, very slowly as the Colorado River gradually incised into the landscape, and eventually over many, many, many years, millions of years, created that gorgeous natural treasure. James Hutton, the father of geology, was convinced that the Earth was very, very old when he would come across outcrops like the one I'm showing you in this photograph. So prior to James Hutton, most people believed that the Earth was about 6,000 years old. But James Hutton would see this type of feature and say, you know what? There's absolutely no way this could have been formed rapidly in 6,000 years. So I want you to take a look at this particular feature and make observations about this outcrop. So pause the video and take a look at the different rocks in this outcrop. Okay, so what you may have noticed here is that some of the rocks are oriented vertically, and then other rocks are oriented not quite horizontal. All right, whoops, that's a wavy line. Anyway, James Hutton saw this and he said, you know what? This type of feature would have needed time for deposition, uplift, and additional deposition. So in the next slide, I'm going to take you through the process that created this particular outcrop that's now known as Hutton's unconformity. And this geometry, this really interesting geologic structure, is the structure that Hutton said basically sealed the deal that the Earth is much older than 6,000 years. Okay, so James Hutton was examining how sediments were deposited, and he noticed that sediments were deposited in oceans horizontally, like this. They were not, or sediments are not deposited in columns. So step one in the creation of Hutton's unconformity is the deposition of sediments. Then what would have to happen? In step two, after those sediments lithified, those sediments had to have been uplifted and tilted, right? To create that vertical geometry. Then what would have to happen next? We'd have to have, in step three, we'd have those uplifted sediments. So they would have been uplifted as a result of earthquake activity. Then we would need to have additional deposition of those overlying sediments. And so when he put the pieces of the puzzle together and he looked at modern day deposition of sediments in the ocean, he said, hey, folks, this outcrop represents a very, very long, extended period of time. It not only involved deposition, it also involved uplift and more deposition. So this is how Hutton's unconformity developed. As we learn more and more about geology and the vastness of time required to build the mountains that we see and create the landscapes that are all around us, we discovered through various geologic techniques as well as using geochemical processes to learn that the Earth is 4.6 billion years old. Now, we'll talk more about the age of the Earth in the chapter on geologic time. We have an entire chapter dedicated to learning how we discovered the age of the Earth, okay? But the one thing about geologic time is that even for geologists who have been studying the Earth for their entire careers, geologic time is so vast, it's incredibly hard to wrap your head around the age of the Earth and how long it has taken for mountain ranges like the Ruby Mountains in Nevada to form. So in intro geology, we will, Albert, come here. Albert, this is my dog, Albert. He's who you're hearing walk around on the deck with me outside here. And Ollie is here too. So they're helping me film this lecture. Okay, thanks guys for your contributions. So it's geologic time is vast, and we talk much more about this in Geology 102. But on the right-hand side of this figure, you'll see the geologic time scale. And the geologic time scale is kind of like the table of contents in a book. and that table of contents tells us about the book's different chapters. Okay, well, the geologic time scale tells us about various chapters of Earth's history. The other thing that, another reason why this geologic time scale is important is because when you're reading a book, if you just open up in the middle of the book and start reading, you're kind of out of context. You don't know what happened before, you don't know what happened after. But with the geologic time scale, it puts things in perspective, and you have a better understanding of what's happened geologically in the Jurassic when you know what has happened beforehand and what has happened after. Let's take some time to talk about the nature of scientific inquiry and the scientific method. All right, so science assumes the natural world is consistent and predictable. So the goal of science is to look for patterns in nature and then use that knowledge to make predictions. So one way that that's used in geology is to find oil deposits. Geologists look for certain types of sedimentary rocks in certain type of structure, and when there's a right combination of rock type and structure, there could potentially be oil deposits. So that's where you would search for oil. Now, scientists, all different types of scientists, collect data through observation and measurement. So observation of the world around us, or in lab experiments, and we use that as we progress through scientific research. How or why things happen are explained using a hypothesis. So a hypothesis is an untested or a tentative explanation. Often, especially in geology, we have multiple working hypotheses, several different explanations for why the Ruby Mountains were formed, or different aspects of how the Ruby Mountains were formed. So a hypothesis that fails rigorous testing are then thrown out, and other hypotheses are generated, or maybe we continue testing those other multiple working hypotheses. A theory is a well-tested and widely accepted view that the scientific community agrees best explains certain observable facts. One of the most famous theories in science is the theory of evolution. So this is a well-tested and widely accepted view in the scientific community. Now, the major theory in the earth sciences is the theory of plate tectonics. Now, plate tectonics is a theory that explains why we see volcanic activity in certain locations, why we see seismic activity in certain locations, and why we don't see seismic and volcanic activity in other areas. And we will learn so much more about plate tectonics in Chapter 2. Let's take a look at scientific inquiry in the earth sciences. A man by the name of Alfred Wegener had the idea that continents moved around the surface of the planet, and he called this continental drift. And although he had incredible evidence to support his idea, he didn't have an adequate mechanism that accounts for how the planets actually drifted. So eventually his idea was discarded by scientists and was considered absolutely radical for its time. But Alfred Wegener is an important figure in geology, and he kind of set the stage for future scientists to take a look at what has become known as plate tectonics, the theory of plate tectonics. So one of the lines of evidence that Wegener used is how South America and Africa look like they fit so snugly together. And he had other lines of evidence that we'll talk more about in chapter 2. But the main reason why his ideas were discarded is he didn't have a solid mechanism that would account for the driving force for how the continents moved. Okay. I did say that I wouldn't record on these learner outcome spots, but this one's a really important one. Describe Earth's internal structure, because this is going to provide the foundation for information about plate tectonics in chapter 2. Okay, so make sure you're really familiar with Earth's internal structure, especially the crust and the upper portion of the mantle. Okay, let's get going. Okay, let's get started with Earth's internal structure. Earth is divided into 3 major layers based on composition. So we have the crust, the mantle, and the core. We'll talk about all of them in depth. So the crust has 2 main types: oceanic crust and continental crust. Oceanic crust is thin and is made of a rock called basalt. Basalt is very dark in color, and it's made up of dense minerals containing a lot of iron and magnesium. Continental crust is very thick, especially in areas where where we have continental collision, like India running into the Eurasian continent, creating the giant, enormous Himalayan mountains. Crust there is 70 kilometers thick, and it's made up of a rock called granite. So granite is located all around me right now. Although the boulders are covered with lichen and organic material, you'll see, I have a little sample here, you'll see that the granite is light in color, and it's made up of a variety of minerals, including quartz and feldspars, and the tiny dark spots are a denser mineral called biotite. And biotite does have some iron and magnesium in it, but for the most part, the minerals and granite itself is a lot less dense than basalt. So it's really important. A good take-home message from this particular slide is that basalt is more dense than granite, and that will be something really important to hold on to for chapter 2 material. I even had a note to myself to talk about relative ages of these rocks. Continental crust is very, very, very old. Oceanic crust is young. So the rocks around me are about 3.5 billion years old, but oceanic crust generally is not older than 180 million years. And we'll talk more about that in chapter 2, but just hold on to that knowledge for now. The other two layers of the Earth, major layers of the Earth, are the mantle and the core. The mantle is located right underneath the crust, and the core is in the center of the Earth. So the mantle is made up of a rock called peridotite, and peridotite is a very dense rock. I believe there's a sample of it in your rock kits, so you can, when you get your rock kits, be sure to take a look at basalt and granite and peridotite. And so the mantle is made up of a very dense material. So peridotite is made up of the minerals olivine and pyroxene, or augite. Augite is the one that's in your mineral textbook, or in your mineral kit. So you should be able to find olivine and augite in your mineral kit. So you can take a look at those minerals, and they are the ones that make up peridotite. Then the core, there are two aspects of the core, the inner core and the outer core. The outer core is made up of liquid iron and nickel, and the inner core is a solid iron and nickel. We use seismic activity generated by earthquakes to determine not only the thicknesses of the mantle, the outer core, and the inner core, as well as the crust, but we can also use those seismic waves to figure out that the outer core is liquid and the inner core is solid. And that is a fascinating story, but it's going to have to wait for an explanation until later on in the semester. You probably will lose sleep over trying, not knowing the exact explanation, but you're just going to have to hold on and be patient because I just can't cover it all today. All right, let's dig into a little bit more about Earth's internal structure. So the Earth is divided by composition, but also by physical properties. And there are two terms here that I really, really, really want you to know: the lithosphere and the asthenosphere. I'm not, super worried that you know more about the transition zone, but the lithosphere and asthenosphere are really important, especially in chapter 2. Okay, so the lithosphere is made up of the crust, whether that crust is oceanic or continental, it doesn't matter, but the crust as well as the upper portion of the mantle, okay? So then that lithosphere, the combination of the upper mantle and the crust, sits directly on top of the asthenosphere. So the asthenosphere is solid, but it's mobile. And the lithosphere is solid and very strong and rigid. The way that I think about the relationship between the lithosphere and the asthenosphere is I think about the lithosphere being the Oreo cookie part of, or the cookie part of an Oreo, and then the asthenosphere is that creamy, delicious, wonderful center, okay? And, well, there isn't another cookie on the bottom, but just imagine the cookie part as the lithosphere, and the, I am getting eaten alive by filming this outside. So the lithosphere is the cookie, the rigid part, solid, and then the asthenosphere is that creamy, delicious, wonderful center. I think I'm going to have to move inside because over the course of filming, since I've moved back out into the grass and rocks here, I think I have like 5 or 6 additional bug bites to my already impressive 2020 summer collection. So I think I'll move inside for wrapping up this chapter. Now that mosquitoes are no longer sucking my blood, let's move on to the rock cycle. There are three main types of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. Igneous rocks are shown in this photograph. We have a nice or several cinder cone volcanoes, and then a really awesome lava flow coming out of the base of this particular cinder cone volcano. Igneous rocks are created when molten rock cools and solidifies. So that can happen inside the earth, or it can happen at or near the earth's surface. So with volcanic activity, that's the molten rock solidifies at or near the earth's surface, and that's a type of volcanic igneous activity. Other types of igneous activity occur deep inside the earth, and that's when rocks solidify in a magma chamber, or as rocks travel from the deep earth interior up closer to the surface. Now, generally, when igneous rocks form inside the earth, they're very large crystals associated with those rocks, crystals that are visible to the naked eye. Now, when we look at rocks like this, these volcanic igneous rocks, those crystals would be really small, and you generally need a microscope to see those crystals. The second type of rock we'll examine are sedimentary rocks. Sedimentary rocks are formed from sediments. Sediments are sand, silt, clay, gravels, any bits of pre-existing rock. So sediments could be derived from igneous rocks, other sedimentary rocks, or metamorphic rocks. Now these sediments come together and they're deposited, and then they end up lithifying into rocks like sandstone. Sandstone is shown in this particular photograph. And this photograph was taken in Zion National Park, showing beautiful ancient sand dunes. Now, these sedimentary rocks accumulate at the Earth's surface, whether that's on a continent or on the ocean floor. Most sediments, very large, thick stands of sedimentary rock are formed on the ocean floor. Now, these sand dunes here were formed in a terrestrial setting in the American Southwest. The third rock type are metamorphic rocks. And metamorphic rocks are really interesting. They're complicated, they're messy. You can see many metamorphic rocks in the Ruby Mountains in northeastern Nevada. That's where this photograph was taken with one of my colleagues from the University of Colorado Boulder. Oh, and you know what? There are some igneous rocks in here as well. This little seam right there is of granitic composition, a granite. That's a type of igneous rock. And this particular igneous feature is called a dike. We'll learn more about those in chapter 4. But anyway, back to the main purpose of this slide, metamorphic rocks. Metamorphic rocks were formed as a result of changing an igneous rock, a sedimentary rock, or even another metamorphic rock into kind of a new rock as a result of increasing the temperature or increasing the pressure. So you could have the sedimentary rock limestone. Limestone is made up of the mineral calcite. And when you increase the temperature and pressure on limestone, that limestone metamorphoses into a rock called marble. So marble has the same chemical composition. It's still made out of calcite, but there were changes within the rock that kind of welded the crystals together to create a metamorphic rock. So heat and pressure are the main players in metamorphism to create that change. The three rock types, igneous, metamorphic, and sedimentary, all come together in the rock cycle. And it doesn't matter where you start in this rock cycle, there are various combinations and paths you can take. Okay, so we've talked about magma chambers and molten material being uplifted to the Earth's surface, forming volcanoes, volcanic rocks. Or the magma chamber could cool and create intrusive igneous rocks like granite. Now these rocks can be exposed at the Earth's surface. So here we have a big chunk of granite exposed at the Earth's surface. And now that it's exposed at the Earth's surface as a result of uplift, it now encounters weather, right? So that weathering of the granite makes it break down into smaller and smaller pieces, or it even breaks down chemically to form sediments. And sediments are shown here. So sediments are those fine particles of pre-existing rock. Now those sediments become lithified, they're cemented together and form sedimentary rock, right? So now those sedimentary rocks could be uplifted, and weathering can occur on those sedimentary rocks. Or maybe those sedimentary rocks are deeply buried and there's an increase in temperature, increase in pressure, and those sedimentary rocks then become metamorphosed into a metamorphic rock. So we will be looking at all aspects of this really interesting rock cycle in chapters 4, 5, 6, and 7. There are some terms listed on this slide and the next discussing features that we see on the Earth's surface. So mountain belts are a major prominent feature that we see on continents, but we also see mountain belts in the middle of oceans. So we'll talk more about that in chapter 2. Cratons, shields, and stable platforms are also important vocabulary to recognize and know. These three terms are often found together. So these terms relate to rocks that are very old and very stable. There's very little active volcanism or seismic activity in these particular areas. All right, a few more terms. Continental margins. These are the areas that are adjacent to major land masses, so the edge of continents. And then moving on to continental shelf, slope, and rise. The continental shelf is a very often large area with a very gentle slope. The continental slope has a very steep slope. And then at the base of the slope, we have the continental rise. And the continental rise is often made up of material that's falling off the continental slope and depositing on the deep sea floor. Oceanic abyssal plains are flat features in the very deepest parts or deep ocean basins. It's not shown here, but deep ocean trenches are areas that are found where oceanic crust is subducting underneath continental crust. We'll talk more about that relationship in chapter 2, but as that oceanic crust subducts or sinks underneath that continental crust, really, really deep trench is formed, so deep that it's actually deeper than Mount Everest is tall. Seamounts are volcanic features that dot the ocean floor. Again, we'll talk more about those in chapter 2. And then, of course, we have oceanic ridges. Oceanic ridges are these mountain ranges that are found on the ocean floor. And these mountain ranges, these oceanic ridges, are giant. They're prominent and they're composed of basaltic rock. So remember, basalt is that material that makes up the oceanic crust.